Venus is a world of crushing pressure and scorching heat, a place where lead flows like water. Yet high above that infernal surface, in the perpetual cloud decks, a radical idea is taking hold. Could life exist there, not on the ground, but suspended in a sky of acid? This is not science fiction, but one of the most urgent questions in modern science. By the end of this exploration, you will understand the compelling evidence that forces us to reconsider what life is and where it can thrive. We will examine a mysterious gas that should not exist and the daring missions preparing to dive into those alien clouds. The search for Venusian cloud life challenges everything we think we know about biology itself. What does it mean for our place in the cosmos if life is next door, floating in a toxic sky? The ground of Venus is a vision of absolute desolation. To stand there would be an instantaneous and catastrophic end. The atmospheric pressure pressing down is 92 times greater than what we feel on Earth. It is the equivalent of being submerged under nearly a kilometer of ocean water, a crushing weight that would collapse a submarine. And the heat, the relentless baking heat, is beyond any earthly furnace. Surface temperatures soar past 460 degrees Celsius, hot enough to soften lead and make zinc flow like water. This is not merely a desert, it is a planetary forge. The cause of this perpetual inferno is a runaway greenhouse effect, a cautionary tale written in planetary geology. Thick clouds of carbon dioxide trap the sun's energy with terrifying efficiency, creating an oven that never cools day or night. For any form of life as we understand it, built from delicate carbon chains and dependent on liquid water, this surface is a realm of pure impossibility. It is a sterilized plain, scoured clean by pressure and heat. This brutal reality forces a profound shift in perspective. If we are to find life on Venus, we cannot look down. We must look up into the very sky that makes the surface a hell. But high above that scorched and silent ground, the story changes dramatically. The sky of Venus is not a single, uniform blanket of poison. It is a world in layers, a stratified atmosphere with its own hidden geography. And within that layered sky, scientists have identified a startlingly narrow band, a potential oasis suspended in the acid clouds. Between approximately 48 and 60 kilometers above the infernal surface, conditions undergo a radical shift. Here, in what we might call the temperate zone, the crushing pressure eases to something remarkably familiar. It feels like the air pressure at sea level on Earth, a comfortable 1 atmosphere. More astonishingly, the temperature plummets from furnace-like extremes to a range between 0 and 60 degrees Celsius. Picture that for a moment. At the upper end of this cloud deck, it could be a pleasant spring day. At the lower end, a chilly but survivable afternoon. This is not the surface of Venus. This is a region in its sky where, purely by the numbers, the environment is arguably more Earth-like than anywhere else in our solar system, aside from our own planet. This band has become the focus of the most compelling hypothesis in planetary science, the proposed aerial habitable zone. It is a pocket of relative sanity in an otherwise insane environment, a place where the physical parameters of pressure and temperature fall within the bounds we know life can tolerate. The stage, against all odds, appears to be set, but a habitable zone requires more than just the right temperature and pressure. It needs a medium, a substance for chemistry to occur within. And here, the Venusian clouds present their greatest paradox, for the droplets that make up these temperate Earth pressure clouds are not made of water. They are composed of concentrated sulfuric acid, a substance that burns through flesh and metal on our world, so we are left with a profound and puzzling equation. How could a zone so perfectly tuned for life in terms of its physical setting be filled with a liquid so universally destructive to life as we know it? The answer may lie in rewriting our very definition of what life is built to endure. sulfuric acid defines the very nature of the Venusian cloudscape. These are not gentle water vapor mists, but a perpetual corrosive haze. The droplets themselves are an astonishing 75 to 95% concentrated sulfuric acid, a brew far stronger than anything found in a car battery. This creates a triple threat for any familiar form of biology. First, it is fiercely acidic, capable of shredding the complex organic molecules that form the backbone of life on Earth. Second, it is profoundly dehydrating, aggressively pulling water from any substance it touches. And third, the atmosphere as a whole is oxidizing, meaning it readily breaks down compounds in a kind of slow, persistent burn. It is a chemical environment designed to dismantle the delicate machinery of life as we understand it. Yet, within this seemingly hostile soup, traces of other ingredients persist. Minute amounts of water vapor float among the acid droplets, along with the dominant carbon dioxide and traces of sulfur dioxide and other compounds. The presence of even a tiny bit of water is critical, as it is the universal solvent for biochemistry, but the overwhelming narrative is one of acid. So the central puzzle deepens. We have identified a temperate Earth pressure zone in the clouds, a physical haven, but that haven is filled with a chemical hell. This forces the question to its extreme. Could anything possibly call this place home? To answer that, we must leave our Earth-centric assumptions behind and journey to the very limits of biological possibility on our own planet. The search for life in an acid cloud forces us to look for a blueprint in the most unexpected corners of our own world. We find it in organisms that do not merely survive in places we consider hostile but truly thrive. They are called extremophiles, lovers of the extreme. On Earth, in the toxic runoff from old mines, rivers flow that are as acidic as battery acid, colored a shocking orange by dissolved iron. To our eyes, these are lifeless, poisoned streams, yet within them, entire ecosystems of microbes flourish. These are acidophiles, life forms that have evolved to not just endure sulfuric acid, but to use its chemical energy. Their cellular machinery is specially adapted to function in a soup that would instantly destroy most other cells. They have built their homes in our planet's chemical hells. This proves a fundamental biological principle. Life is not a fragile accident. It is a tenacious force that can adapt to fill almost any niche, no matter how punishing. But the analogy for Venus requires one more crucial piece. Life in an acid mine is still life on the ground. For Venus, we need proof of an aerial biosphere, life that lives its entire existence suspended in the sky. And remarkably, that proof also exists right above our heads. Scientists sampling the upper atmosphere of Earth have found a diverse community of microbes floating miles high, carried by winds and weather. Bacteria, fungi, and even tiny plants can survive the cold, the radiation, and the dryness for weeks or months, entering a dormant state until conditions allow them to drift back down. This means our own planet has a permanent, floating microbial population. It is a global ecosystem most of us never see, a silent biosphere in the clouds. So when we combine these two facts from Earth, a powerful possibility emerges. We have life that revels in acid, and we have life that lives permanently in the air. The hypothetical Venusian microbe would simply be the ultimate fusion of these two extraordinary adaptations. It would be an aerial acidophile, a floating organism that calls the temperate sulfuric acid clouds of Venus home. This is not a wild fantasy, it is an extrapolation from proven biology on our own planet. The blueprint for life in the Venusian clouds is already written in the rule-breaking biology of Earth. But a blueprint is not proof. To move from a compelling idea to a testable hypothesis, scientists needed a specific, detectable signal, a ghost in the machine of Venus's atmosphere that should not be there. That ghost appeared in the data as a single, stubborn spectral line. In 2020, a team of astronomers made an announcement that sent shockwaves through the scientific community. They reported detecting the chemical signature of phosphine gas in the temperate cloud decks of Venus. On its own, phosphine, a molecule made of one phosphorus atom and 3 hydrogen atoms, might not sound remarkable. But its context is everything. On Earth, phosphine is a gas that simply should not exist in a free, oxygen-rich atmosphere. It is highly reactive and breaks apart quickly. The only places we find it in any significant quantity are in the tanks of chemical plants, where humans manufacture it, or deep in the swamps and intestines of animals, where certain microbes produce it as a waste product. In the natural world, away from industry, phosphine is a fingerprint of anaerobic biology, life that thrives without oxygen. There is no known geological process on rocky planets like Earth or Venus that can produce phosphine in the quantities the team thought they saw. So when that signal emerged from the clouds of Venus, a place with no factories and no animals, it presented a staggering puzzle. Either our understanding of Venusian geology and chemistry was profoundly incomplete, or something in those clouds was making the gas. The implication was as clear as it was unbelievable. This could be a biosignature, a chemical trace hinting at the presence of life. The discovery was met not with celebration, but with intense, rigorous skepticism, which is exactly how good science works. Other teams scrambled to reanalyze the data. Some argued the signal was a misinterpretation, perhaps caused by sulfur dioxide, a common gas in Venus's atmosphere. The original team rechecked their work, and the debate raged in journals and conferences. This controversy is not a weakness of the finding, it is its greatest strength. It forced everyone to look harder. Subsequent observations, including a more targeted look by the James Webb Space Telescope, have so far failed to confirm the initial phosphine detection. Yet, the original team and others maintain there is something anomalous there, a signal that refuses to be easily explained away. The phosphine story, therefore, is not a simple tale of discovery and proof. It is a masterclass in scientific detective work. It highlights the immense difficulty of interpreting a single data point from a world 40 million kilometers away. That one spectral line became a litmus test for our assumptions. It asked a question we still cannot definitively answer: what non-biological process on a hot, rocky, volcanic world could possibly churn out a gas that, on our own planet, is so intimately tied to life? The failure to easily confirm phosphine does not kill the hypothesis of cloud life, it refines it. It tells us that if life is there, its signal is subtle, buried in noise, and fighting to be seen. The phosphine controversy did something more important than provide an answer. It provided a target. It gave the search for life on Venus a specific chemical question to solve. And that question is now drawing a new generation of machines to our sister planet. Missions designed not to gaze from afar, but to plunge directly into the mystery. That single spectral line ignited a scientific firestorm. Detecting a potential biosignature on another world is not a moment for simple celebration. It is a call to arms for skepticism. The initial phosphine announcement was met not with unanimous acceptance, but with a rigorous, sometimes heated, debate that unfolded across journals and conferences. This is how science self-corrects, and the process was as revealing as the finding itself. Skeptics immediately zeroed in on the monumental difficulty of the observation. The signal was incredibly faint, buried in the noise of Venus's brilliant, complex atmosphere. Some researchers argued the data processing itself might have accidentally created the phosphine signal, a kind of digital mirage. They proposed that what looked like phosphine could actually be sulfur dioxide, a common gas in the Venusian clouds whose spectral signature can overlap in tricky ways. If true, it would reduce a revolutionary discovery to a simple case of mistaken identity. Others looked for non-biological ways to make phosphine. Could intense volcanic activity, pumping chemicals from the deep interior into the atmosphere, produce it? While Venus is volcanically active, no known volcanic process on any rocky planet makes phosphine in significant amounts. Could sunlight or lightning striking the clouds trigger exotic chemical reactions we have not yet imagined? Perhaps, but these were speculative answers to a very specific puzzle. The controversy reached a new pitch when the powerful James Webb Space Telescope turned its gaze toward Venus. Its preliminary analysis found no clear sign of phosphine at the cloud tops, dealing a blow to the original claim. Yet, the story did not end there. The original researchers and other teams have pushed back, arguing that the Webb telescope might be looking at the wrong layer of the atmosphere, or that the phosphine could be patchy and variable, hidden in deeper, warmer cloud decks. This back and forth is not a sign of failure. It is the essential machinery of discovery grinding forward. What began as a startling claim has matured into a refined, high-stakes mystery. We are no longer simply asking if there is phosphine. We are mapping the precise boundaries of our ignorance. We are forced to question, what don't we understand about the chemistry of a world we thought was straightforwardly hellish? The debate has transformed phosphine from a potential answer into the most compelling question we have about Venus, and to answer it, we cannot just look from afar. We must go there. The hunt for life cannot rest on a single, disputed gas. While phosphine captured the world's imagination, it is just one piece of a much larger chemical puzzle. Scientists probing the Venusian atmosphere are looking for a symphony of anomalies, a pattern of clues that, taken together, would be far harder to explain without biology. They are searching for the subtle fingerprints a floating ecosystem would leave on its environment. One powerful clue would be the discovery of strange chemical gradients within the cloud deck. On Earth, life does not exist in perfect chemical equilibrium. It constantly pushes its surroundings out of balance. A colony of microbes in a pond will consume certain compounds and excrete others, creating localized pockets where chemistry looks wildly different from the surrounding water. In the Venusian clouds, researchers are looking for similar patches of disequilibrium. Imagine a spacecraft flying through the temperate zone and detecting a sudden, unexplained spike in one gas right next to a drop in another. This could signal a hidden hotspot of activity, a microbial bloom floating in the acid haze, actively altering the soup around it. Another key signature involves unexpected ratios of common gases. The atmosphere of Venus is mostly carbon dioxide with a little nitrogen and traces of other things, but life is a master chemist that can skew these ratios. Certain microbes on Earth, for instance, can process sulfur compounds in ways that change the expected amounts of sulfur dioxide and hydrogen sulfide in their vicinity. If instruments found that the sulfur gases in Venus's clouds were present in proportions that geology alone cannot explain, it would point a direct finger at some ongoing dynamic process, possibly a biological one. Then there is the search for the building blocks themselves, complex organic molecules. Finding simple organics like methane in the clouds would be interesting, but not conclusive, as they can sometimes form through non-living chemistry. The real prize would be detecting larger, more complex organic structures, the kind that typically form the machinery of life, like amino acids or even the complex lipids that make up cell membranes. Finding these floating within the sulfuric acid droplets would be revolutionary. It would suggest not just the raw ingredients for life are present, but that something is actively assembling them into sophisticated structures. Think of it like finding a scattered pile of gears and springs versus finding a fully assembled pocket watch. One is a collection of parts, the other is undeniable evidence of a builder. Together, these clues form a detective's checklist: anomalous gradients, skewed gas ratios, and complex organics. Any one of these would be a major discovery. But if a future mission found all three, aligned in a way that points to a consistent, localized source of chemical activity within the clouds, the case for life would become overwhelming. It would shift the question from "is anything there" to "what exactly is it doing? How does it eat, breathe, and survive in that acidic sky?" The answers would force us to rewrite the book of biology. This brings us to a breathtaking vision, the aerial biosphere. Imagine not a world where life clings to the ground, but one where the entire ecosystem floats. In this model, the Venusian cloud deck is not just an environment, it is the living tissue of the planet. The suspended droplets of sulfuric acid and water become microscopic worlds unto themselves, each one a potential home. Within their liquid confines, protected from the worst of the outside dryness, hypothetical microbes could live their entire life cycle. They would be born, metabolize, reproduce, and die, all while drifting on the eternal winds of Venus. When a droplet grows too large through collisions or chemical processes, it would fall toward the hotter layers below, only to evaporate and release its tiny inhabitants back into the sky, where they could seed new droplets. This creates a perpetual, reigning cycle of life, a closed loop in the clouds. But to sustain such a cycle, these organisms would need an energy source. They cannot eat rock or organic matter from a surface that is impossibly far below and lethally hot. So they must harvest energy from the only abundant resource available in their sky, sunlight. This is where a process like phototrophy comes in. On Earth, photosynthesis uses sunlight to power chemistry, but it relies on chlorophyll and specific wavelengths. In the Venusian clouds, drenched in sulfuric acid, a different kind of light harvesting would be needed. The hypothetical microbes might use the intense ultraviolet radiation that floods the upper atmosphere, a type of light that is harmful to most Earth life. They could possess pigments that capture this harsh UV light, using its energy to drive chemical reactions that combine atmospheric gases like sulfur dioxide, carbon dioxide, and trace water vapor to build the molecules they need to survive. It would be a form of solar power, but adapted for a hellish sky. Alternatively, they might practice chemosynthesis, drawing energy not from light, but from the chemical imbalance of the atmosphere itself. The clouds are rich in sulfur compounds in different states. A microbe could feast on one gas and excrete another, like eating hydrogen sulfide and producing sulfuric acid, tapping the energy released by that transformation. This is exactly what some extremophiles in Earth's acidic hot springs do. In the Venusian clouds, the entire sky would be their buffet, a diffuse soup of chemical energy. This model transforms our view of the clouds from a passive chemical factory into a potential metabolic engine. It paints a picture of a truly alien ecology, one that turns the very things we see as poisons, the acid and the sulfur, into the foundational elements of its existence. It is a life form that would not just endure its world, but would be perfectly, exquisitely crafted by it. But how would such a life actually work day to day in that perpetual sky? We can sketch a speculative but plausible life cycle built from the principles of extremophile biology. It begins with metabolism, the engine of survival. A Venusian cloud microbe would likely anchor itself inside a tiny droplet of sulfuric acid and water, using it as both a protective shell and a chemical workshop. Within that microscopic globe, it might practice a form of aerial chemosynthesis. It could harvest energy by catalyzing reactions between the atmospheric gases dissolved in its droplet, perhaps converting sulfur dioxide into sulfuric acid, and using the released energy to build organic molecules from carbon dioxide and trace water vapor. Every droplet becomes a self-contained biochemical reactor floating in the wind. Reproduction in such an environment would need to be simple and robust. A mature microbe might grow and then divide in two, a process called binary fission, with each daughter cell inheriting a portion of the original droplet's material or finding a new, smaller droplet to inhabit. The eternal, global winds of Venus would then take over, acting as the great disperser. these microbes would not need to move on their own. The planet's super-rotating atmosphere, which circles the globe every 4 Earth days, would carry them around the planet endlessly, mixing populations across vast distances. This creates the possibility of a planet-wide, interconnected biosphere in the clouds, a living layer wrapped around the entire world. Yet this serene floating existence faces one brutal physical challenge: gravity. Over time, droplets collide and merge, growing larger and heavier. Eventually, they succumb to gravity's pull and begin a long, slow descent into the deeper, hotter layers of the atmosphere. For a microbe adapted to the temperate zone, this is a death sentence, so survival demands an ingenious escape strategy. One possibility is that the microbes have evolved a life cycle with 2 distinct phases. For most of their existence, they are in an active, metabolic state, floating and reproducing in their ideal cloud deck. But as their droplet home begins its fatal fall and temperatures rise, they could trigger a dramatic transformation. The microbe might encase itself in a super tough protective shell, entering a state of suspended animation as a spore. This dormant spore would be incredibly resilient, designed to withstand the intense heat and crushing pressure of the lower atmosphere, perhaps even briefly passing through the infernal regions near the surface. Eventually, the droplet would completely evaporate, and the tiny, armored spore, now free, could be caught by rising thermal currents or atmospheric turbulence, carrying it back up into the temperate cloud deck. There, in a new droplet of acid and water, it would reawaken, germinating into an active cell to begin the cycle anew. This spore stage turns a potential extinction event into a necessary part of life's journey, a daring dive into the abyss to seed the skies once more. It is a life cycle of perpetual fall and resurrection, written in the winds of a world without a shore. The search for life on Venus is more than a planetary mystery. It is a direct challenge to our cosmic statistics. For decades, our best tool for estimating the prevalence of intelligent life in the galaxy has been the Drake equation. Conceived by astronomer Frank Drake, it is not a formula with one answer, but a structured series of questions. It multiplies factors like the rate of star formation, the fraction of stars with planets, and the number of those planets in the habitable zone. But the most critical and most uncertain variable has always been this one: the fraction of those suitable worlds where life actually emerges. Is life a near-inevitable chemical outcome on any wet, rocky planet, or is it an astonishingly rare fluke, a one-in-a-trillion accident that happened only here? Our entire view of a lonely or crowded universe hinges on this single number, and right now we have only one data point: Earth. We are trying to guess the odds of a cosmic lottery when we have seen only one winning ticket. This is where Venus changes everything. If we were to confirm that life exists in its acidic clouds, it would not just be a discovery about our sister planet, it would be a revolution for the equation. Suddenly, our single data point of life would become 2, and they would be in the same stellar neighborhood, orbiting the same star. The implications are staggering. It would suggest that the process of life's emergence is not a fragile miracle, but a robust and perhaps common process. If life can start independently on 2 radically different worlds in the same solar system, one a watery blue marble and the other a hellish world with an aerial oasis, then the conditions for its genesis must be far more flexible than we ever dreamed. The variable in the Drake equation for the fraction of planets that develop life would have to be dramatically increased, pushing it much closer to 1. Think of it like this: finding a second tree of life in our own backyard would mean the seeds of life are not rare, exotic seeds scattered by chance across the galaxy. It would mean they are common dust blown on every wind, taking root wherever even the slightest opportunity arises. A living Venus would tell us that biology is not a feature of planets, but a fundamental force of nature, as inevitable on suitable worlds as erosion or volcanism. It would transform our search for life from a question of if to a question of where, and in what astonishing forms it has managed to adapt. the entire galaxy would suddenly feel infinitely more alive. For decades, the only hard facts we possessed about Venus came from a handful of daring robotic explorers. The Soviet Union's Venera program stands as a monumental achievement in engineering nerve. In the 1970s and 80s, a series of their spacecraft plunged through the toxic clouds, deploying landers that touched down on that scorching surface. Against all odds, they survived the descent and transmitted the first, and still only, grainy photographs from the ground. Those images showed a bleak, rocky plain under a diffuse orange sky, a world utterly alien. But while the landers captured our imagination, it was their journey through the atmosphere that provided the first real data on the cloud decks. Instruments measured temperature, pressure, and sampled the chemical soup, confirming the presence of sulfuric acid and the layered structure of the clouds. Yet these missions had a single, brutal purpose: to survive the descent and report from the surface. Their atmospheric science was a secondary objective, a snapshot taken on the way to a fiery conclusion. They were not equipped to look for the subtle chemical fingerprints of life. They were built to endure a hellscape, not to search for inhabitants within it. Around the same time, NASA Pioneer Venus mission took a different approach. In 1978, it sent a multiprobe spacecraft that released 4 separate instrument packages to plunge into different parts of the atmosphere. Unlike the Venera landers, these probes were designed to study the atmosphere all the way down, transmitting data until they were crushed and melted. The orbiter that accompanied them mapped the planet's clouds and weather patterns from above. Together, these missions painted the first global portrait of Venus' churning, super-rotating atmosphere. They mapped the cloud layers, measured wind speeds that howl at hundreds of kilometers per hour, and refined our understanding of the corrosive chemistry. But again, their tools were blunt instruments for a delicate question. They carried spectrometers and sensors designed for bulk atmospheric analysis, not the sensitive detectors needed to find complex organic molecules or trace biosignature gases like phosphine. They were asking what the environment is, not whether anything was living in it. The legacy of these pioneers is a paradox. They provided the foundational map that made the concept of an aerial habitable zone possible by precisely defining the pressure and temperature profiles of the clouds. Yet, by their very design, they left the most profound question completely unanswered. They proved we could reach Venus and gather data, but they also proved how little we truly understood. They showed us a world but failed to see if it was a home. This left a gaping hole in our knowledge, a mystery framed by their heroic data, waiting for a new generation of machines with a very different goal, not just to visit but to truly listen. The silence left by those early pioneers is about to be broken. A new wave of robotic explorers is now on the drawing boards and launch pads, each designed with a singular, revolutionary purpose: to search for the signs of life in the Venusian clouds. This is not a single mission, but a coordinated assault on the mystery. A fleet of spacecraft from international space agencies and even private companies, all converging on our sister planet. Leading the charge are 3 major missions that form a powerful trifecta. NASA Da Vinci+ mission is a daring atmospheric probe. It will not be a lander aiming for the surface, but a sophisticated chemistry lab encased in a protective sphere, designed to survive a 1-hour plunge directly through the very cloud layer in question. As it descends, its suite of instruments will take thousands of measurements, sniffing the air with a mass spectrometer to identify and weigh every molecule it encounters. It will be looking for those critical trace gases, the anomalous ratios, and most importantly, complex organic compounds floating within the acid droplets. For the first time, we will get a detailed, vertical profile of the cloud deck's chemistry, from top to bottom, searching for the chemical gradients that could signal a hidden biosphere. While Da Vinci+ dives into the atmosphere, its sister mission, Veritas, will map the planet from orbit. Using a powerful radar system, Veritas will peer through the thick clouds to create the most detailed global topographic map of Venus's surface ever seen. This is crucial because geology and atmosphere are linked. Veritas will hunt for signs of recent volcanism, mapping hotspots and lava flows to determine if geological activity could be pumping gases into the atmosphere that might explain or complicate the chemical signals Da Vinci finds. Together, they form a perfect partnership, one probing the sky's chemistry, the other investigating the planet's geology. The European Space Agency adds the third piece with its Envision orbiter. Scheduled to arrive in the early 2030s, Envision will carry a different set of eyes. Its spectrometers will analyze the heat and chemical composition of the surface and the atmosphere below the cloud tops at a global scale. It will look for volcanic gases seeping from the ground and study the mysterious, unexplained dark patches that appear in the Venusian clouds, which some scientists have speculated could be vast colonies of light-absorbing microbes. Perhaps most astonishingly, this government-led effort is being joined by private enterprise. The small launch company Rocket Lab has announced plans for its own privately funded mission to Venus. Using its nimble electron rocket and photon spacecraft bus, the plan is to send a small, dedicated probe on a fast trajectory to Venus, aiming to release a tiny atmospheric instrument package into the clouds as early as 2025. This mission would be a focused scout, a proof of concept that could provide early data on cloud composition and acidity ahead of the larger, more complex agency missions. For the first time in history, we are not just sending machines to endure Venus or map it from a distance. We are sending specialized detectives equipped with the tools to search for the fingerprints of life in an alien sky. Each mission carries a piece of the puzzle. Da Vinci is the chemist, Veritas the geologist, Envision the global surveyor, and private scouts like Rocket Labs are the agile pioneers. Their collective data will either build an ironclad case for a living Venus, or it will constrain the possibilities so tightly that the dream of cloud life fades. Either outcome changes our understanding of the universe. We are no longer just observers of other worlds. We have become interplanetary forensic scientists, and the case file for Venus is finally, officially open. Da Vinci Plus is not merely a probe, it is a precision-built atmospheric detective. Its entire mission hinges on a single, harrowing hour, a controlled free fall from the edge of space down through the layered mystery of the Venusian sky. Encased within a rugged spherical descent capsule, its sophisticated instruments will experience the journey firsthand, tasting the air, feeling the pressure shift, and enduring the chemical bath of the clouds. This is not a passive observation, it is an immersive sampling of another world's breath. The heart of the probe is its mass spectrometer, a device of exquisite sensitivity. Think of it as a cosmic scale and sorting machine for molecules. As the capsule plunges downward, it will sip the atmosphere through an inlet, ionizing the gases so they can be weighed and identified by their mass. This instrument will not just confirm the presence of major gases like carbon dioxide. It will be hunting for the trace signatures, the parts per billion whispers of phosphine, sulfur dioxide, and any other anomalous compounds hiding in the mix. It will map their concentrations with vertical precision, creating a chemical profile of the temperate cloud deck from top to bottom. Alongside this chemical sniffer, other sensors will record the temperature and pressure dozens of times per second, correlating each chemical reading with its exact environmental conditions. This is the critical detail earlier missions lacked the ability to say. At exactly 52 kilometers altitude, where the pressure feels like Earth and the temperature is 30 degrees Celsius, the concentration of a certain gas spiked unexpectedly. That kind of pinpoint data can distinguish between a globally mixed atmospheric component and a localized chemical plume, the kind that might billow from a hidden colony of floating microbes. The probe will also carry a camera that will peer outward through a diamond window, capturing the first high-resolution images of the cloud structure during descent. These are not just for awe, though they will certainly provide that. They will show the texture of the cloud decks, revealing whether they are uniform hazes or contain strange, patchy formations, perhaps even capturing the elusive, unknown absorbers, the dark stains in the clouds that have puzzled scientists for decades. Could those dark patches be vast, floating mats of microorganisms, absorbing ultraviolet light as part of their metabolic process? Da Vinci's eye might give us our first visual clue. Every second of its hour-long descent is a precious data point, a note in a song we have never heard before. As it falls, it is effectively traveling back in time, sampling an environment that may hold clues to a completely separate genesis of life. When its work is done, the probe will continue its journey, likely succumbing to the heat and pressure long before it reaches the surface. Its final transmissions painting a portrait of a world that is either hauntingly empty or astonishingly alive. Its data will be the first direct, in situ test of the cloud life hypothesis, moving us from distant speculation to intimate measurement. Yet even the most advanced robotic probe has its limits. It can analyze and measure, but it cannot bring a piece of that alien sky home. For the ultimate, definitive answer, science demands a physical sample. The holy grail of Venus exploration is a sample return mission, a daring quest to capture the cloud particles themselves and bring them back to Earth. The scientific prize is beyond measure. In our laboratories, we have instruments far more sensitive and versatile than anything we can shrink down to fit on a spacecraft. We could subject the samples to a battery of tests, looking not just for chemicals but for structures. We could search for the unmistakable shapes of cell walls, for complex molecules arranged in patterns that scream biology, not random chemistry. We could even attempt to revive anything dormant to see if, given the right nutrients in a simulated Venus cloud chamber, something might awaken. It would be the definitive test, a courtroom where the evidence is presented not as data on a screen, but as a tangible piece of another world. But the challenge of obtaining that evidence is monumental, an engineering obstacle course unlike any other. The first hurdle is capture. A spacecraft must deploy a specialized collector during a high-speed plunge through the atmosphere. This device, perhaps a kind of aerogel trap or a sticky, chemically inert surface, must snare the tiny sulfuric acid droplets without contaminating them, all while enduring extreme heat, pressure, and corrosion. It must work flawlessly in minutes, capturing enough material to be meaningful. Then comes the second, even more daunting phase, sealing and securing the sample. The collector must retract into a robust, multi-layered containment vessel, a thermos bottle from hell. This vessel must maintain a stable, cold environment to prevent the volatile acids and any potential biological material from degrading during the long journey home. It must be perfectly sealed to prevent any earthly contamination from getting in, and more critically, to prevent any Venusian material from leaking out, following the strictest planetary protection protocols. Finally, the sealed sample must survive the violent launch back from Venus, the multi-month cruise through space, and the fiery re-entry into Earth's atmosphere, landing safely for recovery. Every single step is a frontier of technology. We are talking about a mission that would dwarf the complexity of the Mars sample return effort, because we are not picking up a rock from a cold, dry, stable surface. We are trying to bottle a piece of a corrosive, searing, dynamic sky. The payoff, however, justifies the immense difficulty. Holding a vial of Venusian cloud material in a lab would transform the search for life from a detective story told through remote data into a direct physical examination. It would allow generations of scientists to study the sample with tools not yet invented, asking questions we have not yet even thought to ask. It is the kind of mission that defines eras of exploration, pushing our engineering to the absolute limit for a chance to hold a piece of the ultimate mystery right here in our hands. The search for life demands we follow the evidence, but the human mind also loves a compelling story. In the shadows of the scientific debate, a far more speculative narrative has occasionally surfaced, one that speaks to our deepest fascinations with the unknown. It is sometimes called the dark fleet hypothesis. In certain corners of the internet, you might find claims that advanced, unidentified objects have been observed near Venus, a secret fleet of otherworldly craft hiding in plain sight within the clouds. While this idea captures the imagination, it stands entirely outside the realm of testable science. There is no verifiable data, no peer-reviewed observation to support it. It is a modern myth, a reflection of our desire for the universe to be populated not just by microbes, but by star-faring civilizations. For scientists, however, the real mystery is not in fantastical fleets, but in the stubborn, unexplained data from the planet itself. The serious alternative theories are far more fascinating because they force us to expand our understanding of planetary physics and chemistry. If the atmospheric anomalies are not caused by life, what other incredible, non-biological processes could be at work? One strong possibility is that we simply do not understand the full volcanic story of Venus. We know the planet has a young surface, reshaped by volcanism in the relatively recent geological past. Could there be forms of extreme, exotic volcanism we have never seen? Perhaps volcanoes on Venus erupt in ways that spew unusual phosphorus-bearing minerals high into the atmosphere, where sunlight or lightning could then break them down into phosphine through a chemical pathway we have not yet discovered. The planet itself might be manufacturing the gas through a geological recipe we have never witnessed. Alternatively, the answer may lie in purely atmospheric chemistry that operates on a planetary scale. Venus's clouds are a perpetual laboratory of corrosive chemicals bathed in intense ultraviolet light from the sun. Could there be a complex, multi-step photochemical reaction, a kind of atmospheric alchemy that builds phosphine or other complex molecules from simpler ingredients? This would be a natural, if astonishing, chemical factory, one that follows the rules of physics but in a combination we have not yet modeled correctly. There is even the exotic possibility of chemistry driven by the planet's immense atmospheric pressure. In the deep, hot layers below the clouds, under conditions that mimic industrial processes on Earth, gases might recombine in strange ways, forming compounds that then rise into the temperate zone. Each of these alternatives is a challenge to our knowledge, not a dismissal of the mystery. They represent the scientific process at its best, the rigorous exploration of every conceivable explanation before settling on the most extraordinary one. The value of the cloud life hypothesis is that it forces us to invent and test these other theories with newfound urgency. We are not just looking for microbes, we are probing the fundamental, non-living chemistry of a sister world, and in doing so, we might discover that a dead planet can perform chemical tricks we never dreamed possible. The story of Venus may hold a mirror to our own future. This brings us to one of the most unsettling ideas in modern thought, the concept of the Great Filter. It emerges from a simple, haunting question posed by physicist Enrico Fermi. If the universe is so vast and old and life is common, then where is everybody? This is the Fermi paradox, the deafening silence that contradicts our expectation of a galaxy teeming with civilizations. One proposed answer is that somewhere between the emergence of simple life and the development of a galaxy-spanning civilization, there exists a nearly insurmountable barrier, a great filter. This filter wipes out almost every civilization before it can make its presence widely known. The terrifying possibility is that we on Earth might not yet have passed through it. The filter could still lie ahead of us, and here is where our scorched sister planet becomes a profound object lesson. Geological evidence suggests Venus and Earth were likely twins in their infancy, both warm, wet worlds with thick atmospheres and possibly vast oceans. Something happened on Venus, a tipping point was crossed. a runaway greenhouse effect took hold, boiling away its oceans and baking its surface into a permanent furnace. If life ever did arise in those ancient Venusian seas, it was utterly annihilated, its world transformed into a permanent monument to climate catastrophe. This forces a chilling parallel. Is the great filter for many worlds simply the transition from a habitable climate to a runaway greenhouse? Is it the nearly inevitable fate of planets that develop life intelligent enough to alter its environment, but not wise enough to control it? In this light, the search for life in the clouds of Venus takes on a desperate existential urgency. If we find it, it could mean two astonishing things. First, it could mean life is so tenacious it survived the apocalypse of its own planet, retreating to a last refuge in the sky. Second, and more critically, it would prove that a world can cross the climatic point of no return and still harbor life in some niche. That offers a strange, thin sliver of hope, but if we find the clouds of Venus to be completely, unequivocally sterile, the message is far darker. It would suggest that when the climate shifts beyond a certain threshold, the filter closes completely. Life is erased with no second chances. For humanity staring down our own growing climate disruption, Venus is no longer just a distant curiosity. It is a possible future, a time capsule showing the ultimate consequence of a planetary balance pushed too far. Studying its atmosphere is not merely an act of exploration, it is an act of planetary self-defense. We are reading the last chapter of a book to understand how to rewrite our own. This search for life is not without profound responsibility. Every spacecraft we send is a tiny emissary from Earth, and it carries with it an invisible cargo, the potential for microbial stowaways. These are not alien invaders, but our own earthly bacteria, hardy extremophiles that might cling to the craft, surviving the harsh vacuum of space. If such a microbe were to hitch a ride on a probe descending into the temperate Venusian clouds, it could find itself in an environment that, while acidic, might be survivable. The consequences of such an accident would be catastrophic for science. We could inadvertently seed Venus with Earth life, a process called forward contamination. Years later, a follow-up mission might detect life in the clouds, only for us to realize in horror that we were merely detecting our own contamination. We would have turned a pristine alien environment into a biological colony of our own making, forever blurring the line between what is native and what is invasive. The entire scientific endeavor would be compromised, losing the chance to ever know if Venusian life arose independently. To prevent this, space agencies adhere to strict planetary protection protocols. Probes destined for places like Venus undergo rigorous sterilization, baked in ovens, bathed in harsh chemicals, and assembled in ultra-clean rooms to minimize the microbial load. For a cloud mission, this is especially critical as the target is not a sterile, irradiated surface, but a potentially habitable environment. The goal is to send a machine that is as biologically clean as modern science can make it, ensuring any discovery we make is authentically alien. But the ethical equation has two sides. If we one day succeed in a sample return mission, capturing droplets from the Venusian clouds and bringing them home, we face the opposite and equally serious risk: backward contamination. This is the scenario that fuels science fiction nightmares, but scientists treat it with sober, meticulous planning. The concern is not about invading aliens, but about the unknown. A Venusian organism, adapted to a sulfuric acid environment, would be utterly alien to Earth's biosphere. While it is extremely unlikely such a life form could survive or thrive in our water-rich, oxygenated world, we cannot assume that. Its biochemistry could interact with Earth life in unpredictable ways, or it might carry novel pathogens for which we have no defense. The precautionary principle demands we treat any returned sample as potentially hazardous until proven otherwise. This means the sample would not be opened in a standard laboratory. It would be received in a maximum security biocontainment facility, likely more secure than those used for the deadliest earthly viruses. Researchers in full protective suits would manipulate the sample remotely inside sealed chambers, analyzing it with instruments designed to detect life without ever exposing it to our environment. Only after exhaustive testing confirms it is either inert or contains no replicating, threatening biology would the strictest containment be relaxed. These protocols are not about fear, but about respect and responsibility. They are a recognition that we are not just explorers, we are stewards. We have an obligation to protect the integrity of other worlds for science, and an equal obligation to protect our own biosphere, the only one we know for certain supports us. It is a delicate balance between the burning desire to know and the profound duty to preserve. The ethical weight of our search is balanced by a breathtaking vision of human ambition. If microbes could carve out a home in the Venusian clouds, could we? This is not a distant fantasy, but a serious engineering concept studied by organizations like NASA. The High-Altitude Venus Operational Concept, or HAVOC, is a detailed blueprint for a human outpost, not on the surface but suspended in that temperate cloud deck. Imagine not a colony on the ground, but a glittering fleet of habitats, vast metallic envelopes filled with breathable air, floating like silvery balloons 50 kilometers above the inferno. Inside, the environment would be shirt-sleeve comfortable, with Earth-like air pressure and temperature. The view from a viewing port would be unlike anything ever seen by human eyes, a perpetual golden haze lit by a diffused sun, with the planet's surface hidden far below as a distant, glowing ember. This cloud city would drift on the planet's super-rotating winds, circling Venus every few days, its inhabitants living in a sky that never knows night or day as we understand them, but only an eternal, soft twilight. The surreal prospect is that humans might one day live in permanent stations above a volcanic hellscape, looking down upon a world where the ground is more hostile than the vacuum of space. The engineering challenges are, of course, monumental. Every component would need to resist the corrosive bite of sulfuric acid mist. The structures themselves would be lighter than air habitats, using a mixture of breathable air and helium or hydrogen to provide buoyancy, essentially turning an entire city into a floating vessel. Energy would be abundant, captured from the intense sunlight above the clouds, but every resource, from water to building materials, would have to be either brought from Earth or extracted from the atmosphere itself. Breathing air could be manufactured by processing the abundant carbon dioxide, and water might be wrung from the trace vapor in the clouds. It is a vision of a civilization that has learned to live not on a planet, but within its atmosphere, a society of sky dwellers for whom the concept of solid ground is a historical memory or a dangerous frontier. This cloud city would be a testament to human ingenuity, a life raft anchored in the most unlikely of harbors, proving that where life might find a way, so too could we. Living in the clouds is a refuge, but the human imagination has never been satisfied with mere adaptation. We dream of transformation. The ultimate vision for Venus is not a floating city, but a second Earth, a process we call terraforming. This is the stuff of classic science fiction, turning a hellscape into a garden, but could it ever be more than a fantasy? The scale of the challenge is almost beyond comprehension. To terraform Venus, you must solve three interconnected planetary-scale problems. First, you must remove the crushing blanket of carbon dioxide. The atmosphere of Venus is about 96% CO2, a gas that is the primary driver of its runaway greenhouse effect. There is so much of it that its total mass is nearly equivalent to the mass of all Earth's oceans. You are not cleaning the air, you are attempting to dismantle an entire atmospheric ocean. One theoretical proposal involves using giant orbital mirrors to block sunlight, cooling the planet enough for the CO2 to condense and rain down as dry ice, eventually forming glaciers on the surface. But then you are left with a world covered in mountains of frozen carbon dioxide and a surface still baking from internal heat. Second, you must cool the planet down by hundreds of degrees. Even without the greenhouse effect, Venus's proximity to the Sun means it receives almost twice the solar energy Earth does. Reflecting that energy away would require a permanent sunshade of staggering size, perhaps a cloud of reflective particles stationed at the Lagrange point between Venus and the Sun, a construction project on a scale humanity has never attempted. Third, and perhaps most daunting, you need water. All evidence suggests Venus lost its primordial water long ago, the hydrogen stripped away by solar winds. To give a terraformed Venus oceans, you would need to import water, perhaps by redirecting ice-rich comets from the outer solar system on a collision course. The logistics, the energy, and the sheer time required for such an endeavor stretch over millennia, making it a project not for a nation, but for a species with God-like patience and power. Given these titanic obstacles, terraforming appears less like a future project and more like a permanent pipe dream, a testament to ambition rather than a practical blueprint. This realization forces a strategic pivot. If we cannot remake the planet in our image, perhaps we can build a new world within its forgiving sky. This is where the concept of cloud habitats shifts from a research station to a permanent home. Instead of changing the entire atmosphere, we would create small, self-sustaining bubbles of Earth-like environment within it. These enclosed ecosystems would float in the temperate zone, protected from the acid outside. They would grow their own food using aeroponics, recycling every drop of water and every molecule of air. Energy would be limitless, drawn from the sun above the clouds. Over centuries, these individual habitats could link together into vast, floating archologies, entire cities that drift on the wind. This is not terraforming, it is areoforming, building a civilization in the air. It accepts Venus for what it is, a world with a habitable sky and an uninhabitable surface, and it builds within that constraint. This vision is still profoundly difficult, requiring advances in material science, closed-loop life support, and orbital construction. But unlike terraforming, it operates on a human timescale with technologies we can already envision. It trades the impossible dream of a second Earth for the achievable reality of a second home, one that floats in a golden haze, forever looking down on the furnace it wisely chose to leave alone. A discovery of life on Venus would ripple far beyond the pages of scientific journals. It would strike at the very foundations of how we see ourselves in the cosmos. For centuries, human philosophy and theology have often operated on an unspoken assumption of centrality, that our world and the life upon it holds a special, privileged place in creation. Finding a second, independent tree of life floating in the acidic clouds of our nearest planetary neighbor would shatter that anthropocentric view with the force of a revelation. We would no longer be a singular miracle, but one example among potentially countless others. The universe would shift from a stage designed for our story to a vast, humming library of stories, most of which we have never even imagined. This is a challenge not just to our ego, but to our deepest narratives of origin. Many religious traditions contain powerful creation stories that explain the spark of life as a singular, divine act centered on Earth. The discovery of a separate Genesis on Venus would not necessarily disprove these beliefs, but it would profoundly expand their context. It would force a reinterpretation, a broadening of scope. Is the divine creative impulse a one-time event for one world, or is it a fundamental, repeating principle woven into the fabric of reality itself? Theologians and philosophers would grapple with this new reality, debating whether life on Venus represents a second chapter in the same book of creation or an entirely different volume altogether. The implications for our cosmic self-image are equally staggering. Humanity has long wrestled with the question of whether we are alone, a question laced with both profound loneliness and a certain comforting uniqueness. Proof of life next door would decisively end that debate, replacing it with a new and more urgent question. If life is this common, this tenacious, then where does that leave us? Our achievements, our art, our civilizations would suddenly be seen not as the pinnacle of a cosmic plan, but as one possible expression of biology's potential. This is a humbling thought, but also a liberating one. It relieves us of a burdensome cosmic solitude and places us within a community, even if that community is currently just us and some floating acid-loving microbes. It suggests that life, in all its strange and wonderful forms, is not a fragile accident, but a natural and persistent feature of a fertile universe. The silence of the stars would feel less like an empty void and more like a quiet neighborhood where the lights are just beginning to turn on. This philosophical shift would redefine our purpose. Instead of being the universe's sole conscious witnesses, we might become its first explorers, its translators, its gardeners. The duty to understand and protect life in all its forms would take on a galactic significance. Finding neighbors in our own solar system would not diminish our story. It would invite us to begin a new and infinitely richer one, a story of connection in a cosmos that is suddenly, undeniably alive. The discovery of a second genesis in our solar system would fundamentally rewrite the rules of biology. If life can begin not once, but twice, and in two such wildly different environments, it ceases to be a statistical fluke. It becomes a cosmic imperative, a natural and predictable outcome wherever the right conditions persist long enough. The right conditions, however, are the critical part of that statement. For decades, we assumed those conditions meant a rocky planet with liquid water on its surface, orbiting within a narrow band around its star. Venus shatters that narrow definition. It presents a world where the surface is a furnace, but the sky holds a pocket of sanity. If life emerged there, it tells us that the canvas for life's origins is far broader than a warm, shallow sea. It could be a turbulent, acidic cloud deck, a chemical soup constantly churned by winds and lit by ultraviolet light. The process of abiogenesis, the leap from non-living chemistry to a self-replicating system, might be a pathway with many possible entry points. This has profound implications for our search across the galaxy. Currently, when we look at distant exoplanets, we classify them as potentially habitable based almost exclusively on whether they could have liquid water on their surface. We are, in effect, looking for other Earths, but a living Venus would force us to expand that search dramatically. It would tell us to look at the thick, cloudy atmospheres of hot, Venus-like exoplanets, worlds we might have previously written off as hellish and sterile. It would tell us to consider the icy moons with subsurface oceans not just as potential hosts for life, but as places where life might have started independently in a dark, cold sea. The galaxy is filled with a staggering diversity of worlds, many of which do not fit our classic Earth model. If life can start in the clouds of Venus, it can likely start in countless other non-Earth-like niches we have not even begun to seriously consider. This perspective shifts life from being a rare and delicate flower to being a tenacious weed, capable of taking root in the most unexpected cracks in reality. It suggests that wherever energy meets chemistry in a stable enough environment, life will find a way to emerge not as a miracle but as a law of nature. The universe may not be a silent, empty void punctuated by the occasional oasis. It may be a vibrant, living fabric with biology woven into its very structure, waiting for us to learn how to see it. The most profound discoveries are not always about finding what we seek. So we must confront a distinct possibility. What if the clouds of Venus are, after all, completely barren? What if the phosphine signal fades into noise, the chemical gradients prove uniform, and the droplets hold nothing but sterile acid? Would the decades of speculation and the billions spent on missions be a failure? The answer is a resounding no. The search itself, regardless of its final answer, is a transformative act of learning. A definitive finding of no life in the Venusian clouds would be one of the most valuable results in the history of planetary science because it would give us a concrete boundary. Science thrives on constraints, by proving that even in this seemingly perfect aerial niche, with Earth-like pressure and temperature, life did not arise or cannot survive, we would learn crucial limits to habitability. We would understand that the presence of liquid water, even in trace amounts within a solvent, is not enough. We would see that a certain chemical stability, perhaps an absence of overwhelming corrosive forces, is essential. Venus would become a control experiment in the sky, a case study showing us exactly where the line is drawn between a habitable environment and a merely interesting one. This knowledge would immediately refine our search elsewhere. When we point our telescopes at the hazy atmospheres of distant exoplanets, we could say with new confidence, a world with these specific sulfuric acid concentrations and this level of atmospheric turbulence is likely sterile. We would stop chasing ghosts and focus our resources on more promising targets. The negative result becomes a powerful filter, sharpening our entire approach to the cosmos. Beyond the search for life, the missions designed to find it would yield a windfall of pure planetary science. To look for biosignatures, we must first understand the atmosphere in exquisite, unprecedented detail. The same instruments sniffing for complex organics will map the intricate chemical cycles of sulfur, carbon, and other elements with a precision never before achieved. We will learn how Venus's atmosphere circulates, how its clouds form and dissipate, and how its volcanic interior interacts with the sky. This is not just academic. Venus is Earth's twisted sister, a planet that likely started with similar ingredients but ended in a climatic catastrophe. By studying its atmospheric mechanics in minute detail, we are essentially running a diagnostic on a planetary-scale climate disaster. We see the end result of a runaway greenhouse effect in ultra-high definition. Every data point on heat transfer, cloud albedo, and gas retention helps us refine the models that predict our own planet's future. Understanding Venus's weather is, in a very real sense, a masterclass in climate science for Earth. The quest to find life forces us to ask questions we would never think to ask otherwise. We probe deeper, measure more sensitively, and question every assumption. This process, the rigorous, self-correcting engine of scientific inquiry, is the true reward. It teaches us humility, patience, and the profound value of knowing, even when what we know is an absence. A silent Venus would still speak volumes, telling us that life, while perhaps common in the universe, still requires a very specific and precious set of circumstances. It would remind us that our own blue marble, with its vast oceans and gentle skies, is not just one option among many, but an extraordinarily rare and fragile gem. The search does not end with an answer, it evolves because of it. The clock is now ticking toward a definitive decade of discovery. We are no longer waiting for missions to be dreamed up, they are being built. The late 2020s and early 30s are set to become a historic window, a concentrated burst of knowledge that will reshape our understanding of Venus. The first major data could arrive as soon as 2029. That is the year NASA Da Vinci Plus probe is scheduled to complete its one-way plunge into the atmosphere, transmitting its chemical profile of the cloud deck in real time. Its findings will be our first in situ test of the cloud chemistry, a direct answer to the phosphine debate and a search for complex organics. Following closely by around 2031, the Veritas orbiter should be delivering its high-resolution radar maps of the surface, revealing the planet's volcanic heartbeat and its connection to the atmosphere above. Then, in the early 2030s, the European Space Agency's Envision orbiter will join the fleet, adding its global spectroscopic eyes to the effort, mapping heat and chemical signatures across the entire planet. This is not a staggered series of isolated reports, but a synchronized conversation. The data streams will cross-reference and validate each other. Da Vinci Ground Truth will calibrate Envision's global maps. Veritas Geology will explain or complicate the atmospheric chemistry Da Vinci finds. We will see the planet as an integrated system for the very first time. And moving even faster, private missions like the one planned by Rocket Lab could provide an early atmospheric snapshot as soon as 2025, a tantalizing preview of the mysteries to come. This confluence of missions creates a powerful synergy. It means that within the next 10 years, the cloud life hypothesis will face its most rigorous trial. We will either find a constellation of evidence pointing toward a living sky, or we will systematically rule it out. Either outcome is a monumental step forward. This timeline transforms abstract speculation into a tangible waiting game. We are not just hoping for answers someday, we are marking calendars. The great Venusian mystery, a question that has hovered for generations, is finally on the verge of being solved by a fleet of robotic explorers now taking physical shape in clean rooms on Earth. The long silence is about to end. From a world we once wrote off as a scorched and sterile hell, Venus has transformed before our very eyes into the solar system's most tantalizing mystery. We have journeyed from its crushing surface up through layers of corrosive clouds to a narrow band of sky where pressure and temperature whisper of possibility. We have grappled with a spectral ghost of phosphine, debated the limits of extremophile life, and designed robots to dive into that golden haze in search of answers. This is no longer a story about a dead planet. It is a detective story about a world that may harbor a secret biosphere floating in its acid skies. The clues are circumstantial but compelling. A temperate zone in a toxic sky, earthly life that thrives in acid and air, and atmospheric anomalies that refuse easy explanation. Within a decade, a fleet of missions from across the globe will converge on our sister planet, armed with sensors sharp enough to distinguish between geological oddities and biological fingerprints. Their findings will do one of two things. They will either reveal a second genesis of life right next door, forever shattering our cosmic solitude, or they will define the hard limits of habitability, showing us just how rare and precious our own world truly is. Either outcome changes everything, so the next time you see Venus gleaming in the twilight, that brilliant evening or morning star, remember it is not just a distant light. It is a question hanging in the void. It is a world that may hold a mirror to our own fragile existence, or a window into a universe brimming with life. Look up and wonder. The answer